Next, let's talk about an experiment to determine the enthalpy change of neutralization. The enthalpy change of neutralization can be determined by direct measuring the temperature change of the reaction mixture. That is because heat released from the reaction, that means from the system, is equal to the heat absorbed by the reaction mixture. That means absorbed by the surrounding. Okay? Now you are going to carry out this experiment later. That's the experiment. We need a calorimeter. Calorie, okay? Underline C-A-L-O-R, not C-O-L-O-R, not color, calorie, okay? Calorimeter. This is a simple calorimeter. First of all, we have a beaker, and then, we have a expanded polystyrene cup, and then it is put inside a beaker, and inside the beaker we have some cotton wool. All these are used to prevent heat lost to the surrounding. In the beaker we have a stirrer, okay, and then first of all 50 cm cube of HCl is added. Next, pour 50 cm cube of NaOH. Measure the temperature change. Okay. After that, we need to calculate the amount of energy released during the reaction by calculating the amount of energy absorbed by the reaction mixture. Do you understand? After the dilute hydrochloric acid and sodium hydroxide are mixed in the expanded polystyrene cup, the reaction mixture is stirred. The maximum temperature rise is measured. The amount of heat released during the neutralization can be determined as follows by using this equation: mc delta T. M is the mass of the solution of the mixture, C is the specific heat capacity of the mixture, and delta T is the temperature change of the mixture. Understand? And lastly, you need to calculate the number of moles of water formed in the reaction. Okay? And then calculate the enthalpy change of neutralization. Bear in mind, add a negative sign because it is an exothermic reaction. Heat released during neutralization over number of moles of water formed. Understand?
Dynamics, we're constantly trying to measure these quantities of energy that go in or out of the reactions. The question should come up, how do you trap energy and measure it? I mean, moving from out of a reaction, where does it go? How do you catch it and how do you measure it? Calorimetry is the answer to this. It's actually a pretty clever technique. What we do is we take a substance that we know very well how it responds to heat. Our favorite is water. And we're basically going to run a reaction and let all of the heat out or in from that reaction go into the water. What we do then is we measure the water's change in temperature, which allows us to figure out how much heat went into the water, and then we conclude, that heat came from the reaction. So we know exactly how much heat comes out of the reaction. Now, it does require a little bit of planning ahead. You have to build yourself a calorimeter. Now, we have two types of calorimetry. We have constant pressure and constant volume calorimetry. I'll start with the easy one. Constant pressure is the easy one. We'll get to the volume in a minute. Constant pressure calorimetry, we also call it coffee cup calorimetry, which will help you remember that it's super easy to make. When we say coffee cup, what we really mean is a cheap styrofoam cup. Heck, go crazy, get 2 styrofoam cups and stick them in each other. You've got yourself the perfect coffee cup calorimeter. Fill it up with some water. Maybe put one of your reactants in. Maybe you put some acid in it, so it's got acid floating in your cup of water. Now take some base, have a thermometer and pour it in, stir. That temperature will change, especially if you do something like hydrochloric acid plus sodium hydroxide. It's an exothermic reaction, so therefore it gives off heat, and sure enough, the temperature will rise in that solution. And it's real easy to measure the start and the finish. You look at the thermometer before, pour it in, stir, look at it when it stops. You've got yourself a delta T. From that delta T, you simply multiply that by the heat capacity of the water, which is 4.184 joules per gram per degree C, and you multiply it by the mass of the water, which you can easily weigh by sticking it onto a scale. Put all that together and you've got your amount of heat, which we call Q. That amount of heat is what was released from the reaction. That's an extensive property. We know the amount. Now you divide it by how much stuff you used, the amount of heat per gram or heat per mole, and you've got yourself the answer to the actual reaction you just ran. That's coffee cup calorimetry. Easy, cheap. Let's shift to constant volume calorimetry. We call it bomb calorimetry. It's the classic way we measure combustion reactions. It's our favorite thing to put in a bomb. Why do we call it a bomb? Well, you take a stainless steel container, you put something highly flammable in it with a lot of oxygen, and you screw the lid on really, really tight, and then you ignite it. Technically, that's what you do when you make a bomb. Now, for us, we don't want it to explode, so we make sure we don't use enough material to blow the thing to bits. But we do use enough to make it get really hot inside, but the volume is set. So because the volume can't change, there's no work done, which means all the energy is dissipated as heat into the surrounding water. Only problem is it's going to cost you a little more this time, because now you need big container of water, you need the stainless steel bomb, you need something to spark inside the bomb, basically a spark plug, you need wires on it coming out, you need a stir bar, you need all that apparatus hooked together. Oh yeah, an oxygen tank, you got to put the oxygen into the bomb. But once you have all that and you've measured all your quantities, it's no different than the coffee cup. You push a button, it sparks, the reaction goes off, all the heat dumps into the water and the temperature climbs. Once again, you've got a change in temperature that you can change into amount of heat. That's the basis of calorimetry. It works for bomb, it works for coffee cup, and that's how we get the values of delta H for a reaction, and we get delta E for a reaction. So you'll see lots of problems in your book on calorimetry, and it's a really powerful technique on how we get all these values in thermodynamics.